In this video, I'm going to give an introduction and an overview about the Materials and Energy Balance 2 course, your ECH 3024. Alright, and so to give context for this course, let's first think about your MAB 1 course. So in MAB 1, you learned about the conservation of mass. Alright, so you learned that mass is conserved. And so in all of your homework problems and in any of the processes that you now analyzed in that course, you basically operated under the principle that any mass that goes into the system is equal to the mass that comes out of the system. Alright, so that's the conservation of mass. In this course, in MAB 2, what you're going to learn and what you're going to use is the principle of the conservation of energy. Alright? So you'll learn that energy is conserved. Also conserved. Alright? So that any energy that goes into a system is equal to the energy that comes out. Alright? So very simple concept. But in order to apply this principle, we first need to define what energy is. So what is energy? Right? I'm sure this is a word that you've heard about quite a lot. You know, you hear it in the news every day, and you've probably talked about it in person. But what is it? What is energy? The working definition that we're going to use in this course is that energy is the quantifiable capacity to do work. So quantifiable capacity to do work. Alright? So if you want to complete your work, you need to have energy. This is a fairly simple definition, but energy itself is a very complex phenomenon. Energy exists in many different forms. Alright, so it exists in many different forms. Some types of energy that we're going to learn about in this class include mechanical, thermal, chemical, and electrical energy. But those aren't the only ones that exist, and there's basically almost infinite amounts of forms of energy in the universe. Essentially, though, you could sort of associate any form of energy with movement. Associated with movement. So with mechanical energy, you could think about the movement of pistons or motors and rotors. With thermal energy, you could think about the movement of molecules at the microscopic scale and how fast they move. With chemical energy, you could think about molecules transforming from one thing to another. And electrical energy, you could think about the movement of electrons. All right? And so all forms of energy you could just associate with movement. And one of the most interesting things about energy is that it could transform from one type to another. Transform from one form to another. Okay? And so one example of this, that drawing back on your MAB1 experience, is let's say you have some sort of combustion reaction going on. Alright? So you're reacting, let's say, methane with oxygen to form carbon dioxide and water. Right? But with that reaction, it's not just the actual chemical species that are important, but it's the actual energy that is released from the reaction that is useful. And so this combustion reaction is going to release some energy, some chemical energy, that's then used to heat some steam, and by heating that steam, it makes it move faster, right? And so this fast moving steam is then used to turn a turbine, right? And that turbine, from its spinning, helps produce electricity. Okay? Alright? And so, over the course of this entire process, right, we're taking thermal energy from the combustion reaction and we're turning it into, or we're taking chemical energy from the combustion reaction and then we're turning it into thermal energy, which we then convert into mechanical energy, and then finally we use that as electrical energy, right, which we can then use to power all of the processes in our daily lives. All right. And so the fact that energy can move from one form to another is not only important in the context of a combustion reaction, but it's also critical if we're trying to develop technologies, for instance, to convert solar energy into electricity, or even the moving river into electricity that we could use in our lives. All right? And so energy is an important thing. All right? And so in this course, what we're going to do in ECH 3024 is we're going to learn how to calculate the energy transfer and the energy costs that are associated with different sorts of processes. So we will learn how to systematically calculate energy costs of any arbitrary process. Okay? And when I mean arbitrary, I mean we're going to span many different fields. Industrial processes, biological processes. We may even go to space and talk about cosmological processes as well. And there's many more that we'll encounter in this course. But even more so than just, learning how to analyze different processes, we're also going to learn about different sort of physical concepts that control energy transfer throughout the universe. So we'll introduce physical concepts that control energy transfer. All right? And all of the physical concepts that we learn are going to fall under the umbrella of thermodynamics. Right? And so we'll get more detail about that later. But essentially, in this course, here's what the breakdown is going to be. Alright? And so 70% of this course is just going to be focused on problem solving. Alright, so during the in-person class time, we're mostly just going to be focused on solving different types of example problems. Okay? And what I'm going to emphasize is the conversion of the problem text into the actual math and physics that you need to use in order to solve the problem. /physics. Okay? So that's going to be 70% of the course. 25% of the course is going to be details of how the thermodynamics work. All right? So we'll learn about things like heat capacities and Hess's law. A lot of laws. We're going to learn about a lot of laws in this course. All right? So 25% of how the thermodynamics work. But in order to give you context for the importance of what you're doing, I also want to spend some time talking, giving a few history lessons about the development of the concept of energy and how developments in energy research have transformed life as we know it, transformed society. Okay? And so this is going to be the course breakdown for this class. So in this course, we're going to focus on how to develop energy balances. But that doesn't mean we're going to ignore the material balance side of the equation. In fact, in order to solve for the energy balances that we'll encounter in this course, we'll actually have to develop and solve before, or maybe solve at the same time, the material balance. All right? And that's because material and energy balances are interrelated. So material and energy balances are interrelated or intimately related, if you will. Okay? And to demonstrate or illustrate this synergy between the two, I want to go through a couple of examples with you. Okay? So the first example is going to tie back to what I mentioned previously, which is the combustion of methane. Okay? And so let's go into this in a bit more detail. And so, with the combustion of methane, let's write out the chemical reaction, right? So we have 1 mole of methane reacts with 2 moles of oxygen gas to form carbon dioxide and 2 moles of water, all right? And so that's the reaction that goes on. But let's say we design a reactor in which we have this reaction occur. Okay? So in the feed stream, stream 1 over here, let's say I have some moles of methane, and then I also have some air fed in, which contains oxygen, but air also contains the inert nitrogen as well. Alright? And so this feed goes inside a reactor that's at a temperature of 632 degrees Celsius and a pressure of 1 atm. Right? And so in the product stream, in our nominal product stream, we're going to have some carbon dioxide. And we'll say that this reaction, all the methane and oxygen, those are fed in stoichiometric amounts and they react completely. All right. So we're going to simplify it a bit just for this example. But basically in our product stream, we're going to have carbon dioxide, water, and then also that inert nitrogen. Okay? All right, but as I mentioned before, with combustion reactions, usually we don't really prioritize the actual chemical species that are coming out. Right? That's not our main goal. Our main goal is to harness this reaction so that it produces energy. Okay? So, with this reaction, it's an exothermic reaction. And so we're going to have, that means we're going to have energy leaving the system. Okay? And so, reaction is exothermic. Right? And so, in other words, we have what I'll say, well, actually, I won't write the word heat. All right, energy is released. Okay? And the amount of energy that's released is something that is already well characterized through years and years of research. All right? And so the amount of energy that's released from a combustion of methane reaction is 52 kilojoules per gram of methane. Okay? So this number, it's 52,000 joules per gram. It may seem like a lot, all right? But to give you some context, if we compare this energy density to, let's say, the amount of energy that's stored inside a chicken McNugget, you'll see that it's only 4 thousandths of the amount of energy that's stored inside a chicken McNugget. All right? Energy density of a chicken McNugget. All right, so the reason I bring that up is because if you're running, this sort of combustion of methane process in order to produce energy for an entire city, you know, you're not going to use just 1 gram of methane. All right, you're going to use a lot of methane, right, in order to provide enough energy. All right, and so that's because the energy leaving the reactor can be converted into other forms of energy. The energy from this combustion reaction is used to heat steam, which is used to turn a turbine, which then generates electricity for the city. All right. And in order to power your city, all year round, you need to continuously feed in methane, right? Because the more methane you feed into your process, so the more methane that reacts, the more energy is released. All right. And so I want to highlight that. Right? It's 52 kilojoules per gram, and so you're going to need to continuously feed in lots of grams of methane in order to power your city. So that was a sort of industrial example of how energy balances are important. But as I mentioned before, energy is important at all length scales in the universe. And so I want to go through another example where we're going to work on the microscopic scale. And we're going to talk about something that I'm sure you've heard quite a lot about over the past year, which is the COVID-19 vaccine. Okay? All right, and so just to give a very, very simplified primer on the COVID-19 vaccine. All right, and so a coronavirus is a virus which has these little spikes on the surface. Okay? Okay? And these spikes are important for the function of the virus because they help the virus trick its way into cells. Alright, so these spikes sneaks virus into cell, essentially. Alright, and so clearly it's not good if the coronavirus gets into your cells and then allows itself to start replicating and get you sick. Alright, so we need to develop a vaccine. And so, in contrast to traditional vaccine approaches, in which they basically would just inject a weakened form of the virus into your body, what the current, at least corona or COVID-19 vaccines are doing is they're trying to get our cells to make spikes for us. All right? And the reason we're doing this is because we want to train our immune system to recognize these spikes. And once they could recognize them and realize, oh, this is like a bad thing that we're seeing, also train the immune system to destroy the spikes and the corresponding virus. Okay? And so that's what the COVID-19 vaccines, at least the major ones, that's the principle that they work on. All right? And so what I want to focus on is the actual process involved in getting the body to make these spikes. Okay? And so what we're going to focus on is in each of your cells, you have what's known as a ribosome. You may have heard about this in your biology class, but basically, the ribosome in your cells, they make proteins. All right? And in order for them to make proteins, they need a set of instructions. All right? And so, with the coronavirus vaccine, basically what it's doing is we're delivering these instructions to our cells. Right? And these set of instructions are known as RNA, right? Or mRNA for the mono. All right? And so RNA is a set of instructions for making proteins in general. They're just instructions for making proteins in general. But the RNA that we're delivering to our cells with the vaccine is the instructions for making the spike protein. Right? So the ribosome gets these instructions, right? And once it gets in the instructions, it then collects the ingredients it needs to make the spike protein. And those ingredients are known as amino acids. And once it has all the amino acids it needs, it then would want to make the spike proteins, right? But in order to do that, even though it has all the ingredients, the other major thing it needs is it needs actual energy in order to make it, right? Because each time it connects these amino acids together, it requires some sort of energy in order to get the reaction to proceed, all right? So the ribosome needs energy in order to form the spike protein, and it gets that energy in the form of ATP, which you may have heard in your biology class. So ATP is adenosine triphosphate. All right? And so the sort of reaction that produces this adenosine triphosphate is a bit complex, right? But basically, you get this ATP from the food that you eat. Okay? And so what I want to emphasize here is that in order to get your body, or to get your cells to make these spike proteins, it's not enough just to have the mRNA from the vaccine itself, but you also need energy from the food that you eat in your body in order to make the spike protein. Okay? And so, really, the production of the spike protein in order to fight the COVID vaccine is just another example of the many sorts of processes that occur in your body that rely on energy that you get from the food that you eat. So digestion of food releases energy needed for regulating the immune system, as we see with this vaccine example. But you also need energy just to regulate your body temperature. Keep it at that cool 37 degrees. Right? And there's hosts of other biological processes that rely on the energy provided from the adenosine triphosphate. Processes. Okay? And so here was an example at the microscale of processes that rely on the transfer of energy from one form to another. Right? But the analytical framework that I've sort of presented, both in the combustion of methane example and also in this vaccine example, these are just a very general framework, right? Basically, I drew boxes each time and then drew arrows to represent the different things that were going in and out of those boxes, right? And so this analytical framework that I'm applying here It doesn't just work for those examples, but you can generalize it to any sort of physical system that we deal with in this course. Alright? And so the box that I drew up there was a ribosome. And we could expand it a little bit and make it even the cell. Or we could do analyze processes in which our system is the sky. Or we could go even bigger and analyze processes in which our system are galaxies. Nevertheless, regardless of what the size of our box is, in order to sort of at least get a rough estimate of the energy transfer processes that are occurring, we could apply the same strategies that you'll learn about in this course. Okay, and so I've talked about sort of in general terms about energy transfer from one form to another. But one of the major things that you're going to learn about in this course is that the transfer of energy just by itself, there are going to be some costs associated with it. To demonstrate this, I want to return to the combustion of methane example that we discussed previously. In that previous discussion, I sort of simplified it and presented an ideal system in which the methane and oxygen are fed in equal molar amounts and are consumed completely, and so that the only things that come out are CO2 and water. All right, but usually in actual real processes, you're not going to have complete conversion, right? You're either going to feed things in non-stoichiometric amounts, and your reaction is not going to proceed to 100% conversion. And so some reasons for that, or at least consequences of that, is so instead of just having the CO2 and water come out, you're also going to have some CH4 and O2 come out. But in addition to that, you're not just going to have your main reaction go on, right, which was the combustion of methane into carbon dioxide, but there's also going to be some side reactions that occur. Right? And so with these side reactions, they're not producing CO2, but they're going to produce things like carbon monoxide or sulfur dioxide or even nitroxides as well, with some variable amount of oxygens. And there's many other side products that form, just because the feed stream isn't going to be pure methane and air, right? There's going to be some impurities in there that will react and form these other products. And the reason I'm highlighting these other products is because they belong to a group of chemicals known as greenhouse gases. All right? And so the emission of these chemicals are responsible for many of the climate change issues that we're encountering today in our society. Okay? And so, with not just the combustion of methane, but even just a lot of processes that are going on in the world right now, one of the main things that we're trying to do as a society is trying to limit the emissions of all these greenhouse gases. Goal of limiting emissions. Okay? But that's going to be a challenging thing to do, right? Because this ties back to what I mentioned earlier. If we want to produce more energy, we need to, consume and react more fuel, right? And based at least on early estimates, our consumption of this fuel is only going to go up because energy demand is only going to go up. So natural gas consumption, for example, will increase by 40% over the next 30 years. Okay? Right? And so that's just the energy, or that's just talking about the things that are consumed directly in this combustion reaction process. But furthermore, I simplified it just by drawing a black box and saying it's at a temperature of 632 C. Well, that's a fairly hot temperature, right? And so in order to get this process at that temperature, we're going to need to heat it somehow, and that heating is going to require energy itself, right? And so energy is going to be needed to heat and run the reaction process, right? And in order to get that heat, we're going to need to burn other things as well. And you could see how um, this process, even though we're just looking at a very simple reactor, is already going to become more complex, right? Another thing I'll mention is that, this combustion reaction is releasing energy, but not all of that energy is going to be directly converted into electricity, right? And there's going to be many sources of energy loss before electricity even reaches the customer, right? And so what I'm saying here is that the efficiency of this sort of process is not 100%. More likely, it's going to be only about 20% of the energy produced by this reaction is actually going to reach the customer. Okay? And so there are a lot of costs associated with just the transfer of energy from one form to another. And not just inefficiencies in the process, but also some costs that, irreparably harm our environment and society as well. Okay? And so you probably noticed that there's been a big movement recently to try and change our habits so that we, you know, consume and generate energy in a more efficient and sustainable manner, right? And so we must figure out how to transfer energy in an efficient manner and sustainable. And we'll talk more about that throughout this course, right? But the main thing I want to emphasize is that in order to achieve this goal, engineers will play a central role, right? We will be the ones designing the processes uh, that produce energy in an efficient manner, and we'll be the ones, figuring out how we could convert existing processes so that they could be more sustainable. All right. So this course, while it does, just from the name, imply that we're focusing just on how to derive energy balances, everything you'll learn in this course is going to be basically the foundation for the rest of your career.